In this lesson, we're going to start looking at actual trig functions. You've learned about trig functions back in grade 11. However, when you did it then, you did it in degrees. Now we're going to use radians as our unit of measurement, since that is going to be the focus of this course. So there are actually 6 trig functions. There's the 3 primary ones, sine, cos, and tan, and then the 3 reciprocal ones, which are cosecant, secant, and cotangent. Just to get us warmed up, let's take a look at the sine function in degrees the way you know it. So as you can see, this axis here is measured in degrees. The y-axis is just the output value. It's not in any angle measurement. It's just whatever our output is. So if you remember what the sine graph looked like, it had a maximum value of 1. Let's put that there. And a minimum value of -1, and it's what's called a periodic function, so it repeats. And so it starts at the point 0, 0. At 90 degrees, we get our maximum value of 1. At 180, we get back to 0. We get our minimum at 270, which is -1, and then we're back at 0 again, or 0 on the y-axis at 360 degrees, and it starts over, and that's what's going to make it periodic, is we would just keep following this wave type pattern where it goes up and down forever. Okay, that's the basic sine function shape. Remember what the amplitude is? The amplitude is the distance between the axis of the curve and the maximum or minimum point. And so in this case it's 1. The period is the length of one cycle. So you can see here that one cycle before it repeats is 360 degrees. The range is going to be what values are allowable. So it is all real numbers again. So y is a member of the set of real numbers. But it's got a minimum. It can't go below -1. It can't go above +1. So y has got to be greater than or equal to -1 and less than or equal to +1. The domain is all real numbers. Sometimes we would say that it's, if it's restricted between 0 and 360 degrees, I might put that in there, but for this function, it really does keep going forever, and I'll indicate that with arrows on the end. All right, so that's our basic function. Let's do it again in radians. So now you can see that instead of having degrees on this horizontal axis, we got radians. It goes up to 2 pi because we saw that 2 pi was like 360. And in fact, everything matches up. Pi would be the same as 180. Pi over 2 would be the same as 90. 3 pi over 2 would match up with the 270. So we're familiar with these conversions after last lesson. It still has a maximum value of 1 and a minimum value of -1. And it still follows the exact same pattern, which I can map out like this. And it looks exactly the same. The only thing different, again, is the units on the x-axis. The amplitude is still 1. The period is, because we got different x scale, it's going to give me different periods. So in 360 becomes 2 pi before it repeats. The range is going to be exactly the same though, YER, where y is greater than -1, greater than or equal to -1, less than or equal to +1, and the domain is still all real numbers. So, the only thing different between these two graphs is that the x-axis scale is in radians. Only difference is x-axis is measured in radians for the second one. Okay? So that's the sine function, and that's it in radians. Cosine function, you may remember, uses the same maximum of +1, minimum of -1, still has one full cycle in 360 or 2 pi degrees, or 360 degrees, or 2 pi radians, I should say. But it starts at 1, the maximum, hits the x-axis at pi over 2, the minimum at pi, x-axis again, and back where we started at 2 pi. So it's got that same wave form to it, but it just starts at a different place. And the amplitude is the exact same. The amplitude is still going to be 1. You know, the amplitude we can measure anywhere. It's between the axis and the maximum or minimum point. The period is still 2 pi, 1 full cycle. It's starting over after 2 pi. The range is exactly the same. YER greater than or equal to -1, less than or equal to +1. And the domain is exactly the same again. Okay, so a lot of similarities between the cosine function and the sine function. It's like you took the sine function and shifted a little bit to the right or to the left. The tangent function is a little bit different, and it was one that we saw, if you remember from grade 11, didn't have that wave shape to it. And it, in fact, had asymptotes. The tangent function, by the way, you may recall, is equal to sine x over cos x. So it's like we put one of those functions on top of another one and saw what kind of, like a rational function, like we've seen a few lessons ago, and got this new combined function. And that new combined function is going to have, because it's a rational, at least when we think about it that way, we'll have some asymptotes. The asymptotes occur at pi over 2 and 3 pi over 2. So we got these vertical asymptotes that the graph can never touch. And it starts at 0, 0, but then it goes up very quickly, and it's going to go up towards infinity as it gets closer and closer to this asymptote. Then immediately on the other side of the asymptote, it comes up from negative infinity, steeply, starts to flatten out a bit, almost like a cubic function when it hits the x-axis at pi, and then starts to swoop upwards again as it gets closer to the next asymptote, which is 3 pi over 2. And then it just carries on this pattern over and over and over again. So this is the shape of the tangent function. The amplitude, the distance between the axis, the x-axis, and the maximum, well, there is no maximum since it goes up to infinity, so it does not exist. D and E does not exist. The period, before it repeats, is just pi. It's not 2 pi this time. You can see 1 full cycle right here. This is 1 cycle. This is part of 1 cycle. This is another part of 1 cycle. But 1 full cycle is this one that I've outlined in red. You can see it. It goes from pi over 2 to 3 pi over 2, which means that it's actually pi radians in length. The range is all real numbers. It goes up forever and down forever, so you can get all possible y values. The domain is all real numbers except where the asymptotes occur. So the domain is xer, but it cannot equal, x cannot equal pi over 2 or 3 pi over 2, and since it repeats, it would be 5 pi over 2, and in fact, we could stick some negative ones in there as well, because we know it goes to the left as well, so we can include negative pi over 2, negative 3 pi over 2. I don't have room to write that, so I won't. And the asymptotes are just the same as what's not allowed here. The actual asymptotes are those equations. So the asymptote would be, again, negative 3 pi over 2. I'll actually write them in this time. It would be negative pi over 2, positive pi over 2, positive 3 pi over 2, and so on. How can we determine the location of the vertical asymptotes? Well, since it is, as I mentioned above, tan equals sine over cos, we know that we're going to get an asymptote anywhere we have division by 0. when are we going to have 0 on the denominator? Anywhere that cos equals 0. So wherever y equals cos x equals 0. And if we look back at the cosine graph, oh, there it is right there, we can see that the cosine graph equals 0 at pi over 2 and 3 pi over 2, and then it would do it again at 5 pi over 2 and 7 pi over 2 and so on. So that's an easy way, if you can remember this relationship, to know where the asymptotes are for the tan function. Those are the three primary trig ratios. Then we have the reciprocal ones. So we've seen reciprocals back when we were looking at rational functions. And the first reciprocal we're going to look at is cosecant. Cosecant is the reciprocal of sine. So if I take a sine function and flip all the y values, do 1 over all the y values, I'll get a cosecant function. So it's easiest to do a cosecant function if I just sketch the sine function first. So I'll do that in, I don't know, I'll do it in blue. So again, 0, 0, pi over 2, 1, and so on. Here's my sine function. Doesn't take long to get a little sketch going there. But now I'm going to take each one of these y values and do 1 divided by it. So let's start with this point here, the origin, 0, 0. The y value is 0. 1 divided by 0 is undefined. So we're going to have an asymptote here at this point. In fact, anywhere that y equals sine x crosses the x-axis, we're going to have an asymptote. Because for each one of these points, we're going to have a y value of 0. So we're going to divide by 0. So we have 3 asymptotes that you can see here. Now if I take each of these different y values, say I take this one here, where the y value is 1, if I do 1 over 1, I get 1. So this point will stay the same. Say I take this one here, which is about a half here. This one's about a half. 1 divided by a half actually equals 2. So I'm going to get the point 2, the y value of 2 up here, likewise here. And so what we're going to get is a graph whose lowest point comes down to positive 1, and it's only going to go up towards infinity from here. And then the other part of the graph on the right-hand side of this same graph, I'm going to have, if I take this point, I'm going to do 1 over negative 1, which is still going to equal negative 1, so this point will stay the same. I'm going to do 1 over negative a half, so that'll become negative 2, and we can quickly see that we're going to have another section of the graph that looks like this. Now we've got these 2 parts of this graph, and we have to take both of these parts for 1 cycle. So I need an upward-facing part and a downward-facing part for 1 cycle. And we can see that it requires a period of 2 pi in order to do that. So I might as well fill that in now. Our period is 2 pi. Our amplitude is another one of those ones where it goes up forever, so there can't be an amplitude. It does not exist. The range is a bit different. Now the range is y is greater than or equal to 1, or y is less than or equal to negative 1, and it's YER. There's just not a lot of room to write these things in here. The domain is all real numbers, but again, we've got the asymptotes. So x cannot equal anywhere there's going to be an asymptote. So at 0, at pi, at 2 pi, but it would also go, negative pi, negative 2 pi, 3 pi, all these other places as well. But I don't have room to write them all in, so I'll just write a few of them in. And the asymptotes, again, are wherever the restrictions were in the domain. So 0, pi, 2 pi, 3 pi, etc., negative pi. So there is our cosecant. And just like cosine is just a variation on sine, secant is just a variation on cosecant, because secant is 1 over cosine of x. And so, again, let's start with a sketch. Let's have this be positive 1 and have this be negative 1. And we're going to start at 0, 1, and we're going to we'll sketch the graph of cosine first off, and then we'll do the reciprocal like we did for cosecant to get the secant graph. But we can be faster again. Where the asymptotes, they're going to be at pi over 2 and 3 pi over 2 because that's where the zeros are on cosine. And we're going to have our lowest point for this section at 1, and it's going to go up from here. And it's going to be, if I go to the other end, it's going to be up from here. And then in the in-between part, it's going to start at negative 1, and again, it's going to go down from there. So same shape, but it's just been shifted a little bit to the left or right, depending on how you look at it. Amplitude, again, does not exist. Period, it's 2 pi. It starts over. It's sort of hard to see it because it's the pieces of the graph, there's 3 chunks of the graph we can see on our vision here, but if we were to expand this out, we'd see that it's repeating every 2 pi units. The range is exactly the same as for the cosecant, so it's YER, but y has to be greater than or equal to 1, or y has to be less than or equal to negative 1. The domain, again, is all real numbers except where the asymptotes are, so x cannot equal pi over 2, or 3 pi over 2, or 5 pi over 2, or negative pi over 2, and so on. The asymptotes are just all the places that the domain can't hit. Okay, the last one is the cotangent function, and remember cotangent is equal to 1 over tangent. And if tan equals sine over cos, then cotangent must equal cosine over sine. So there's a couple ways we can approach the cotangent function, but I think the easiest way is just to, again, flip the tan function. So let's see, let's draw out the tan function again. We had it up here, right? So we had our asymptotes. Actually, you know what? I'm going to backtrack. I'm not going to do it that way. I'm going to use this. I'm going to use cos x over sine x. So I'm going to find my asymptotes by where does sine x have zeros, because we're going to start with that. Here's sine x. It has its zeros at 0, pi, and 2 pi. So let's draw some asymptotes there because we know that the cotangent function will have its asymptotes in the same place. So 0, pi, and 2 pi. And as far as the graph goes, it actually looks really similar to a tangent one, but again, it's 1 over. It's like we did 1 over each part. So it's going to basically make it look like it's flipped upside down, and you can check this on Desmos as well. If you type in y equals cotangent x, it should graph it for you. And you're going to find it's got the same swooping look to it. The only difference is that the swoops are coming down from the left rather than going up to the right. So this is the basic shape of the cotangent graph. The amplitude, one more time, it's no maximum, so there can't be an amplitude, does not exist. The period, as you can see, it repeats every pi units. The range is going to be all real numbers. The domain is going to be all real numbers, again, except for the restrictions. And the restrictions, oops, that should be an x, not a y. And the restrictions are going to be where the asymptotes are, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, negative pi. Again, I'm not writing them all down because there's an infinite number. So let's write a few of them down. Negative 2 pi, because it will be there. Negative pi, 0, pi, 2 pi, and so on. All right, here is a summary of all the reciprocal ones. The last three we did, so you got it all in one place. Here are some key ideas which you can take a look at and read those over on your own. And then, as usual, there's some practice. Here's the practice questions here.